from Intel, but formerly from University of Washington, who's going to present us Finexus, which is tracking precise motion of multiple fingertips using magnetic sensing.
Extra.
It should be fine.
Yeah. Sorry for waiting. Debug all the time. All right, hi everyone. My name is Chen from Intel Lab. Actually, I'll join them officially next week, so I'm employed for now. So today I'll present our work, Finexus. It's an input device that can track your fingertip in 3D. And this is my summer internship project at Oculus Research with my mentor, Keller, before I graduated from University of Washington, and also with my advisor, Shwetak Patel, from UBCOM lab at UW. I think in the past couple of years, we have seen so many different wearable devices, including some smartwatch or a different type of glass. And this device extends our experiences beyond traditional interaction, and I think they're really good. And input to this type of device usually relies on either voice or small touch area to enable some simple tasks, like playing music or browsing photos. And of course, with SIGCHI, we have more capability for now. But I think people now still looking for a better way to interact and use these devices. And this issue becomes even more challenging when people start to use head-mounted display like Oculus Rift or Microsoft HoloLens. Instead of detecting those simple and discrete hand gestures, people using VR or AR are looking for a way that can continuously track your hand and fingers so they can better manipulate and play with those objects in a virtual space, just like what we get used to do in the original physical world. So some existing approach usually involves a 3D camera that you can directly attach on your display right here, or an IMU with a handset form to track your hand motions. But they usually suffer from some kind of occlusion because it requires line of sight, or can only track very coarse and hand motion. There are, of course, the many different sensing approach that shows very successful, but we still see a research gap there, and there's some limitation to overcome. And that's why we try to explore an alternative approach. In particular, we look for using magnetic field sensing for finger tracking. So we target a device that is occlusion-free and can track fine-grained and delicate finger motion in 3D. And this is where the project Finexus came from. Finexus is a 3D input device that can track multiple fingers using magnetic field sensing. So by putting this one-dimensional electromagnets on the back of your fingernail, the system can robustly and accurately track your fingers' motions using only 4 magnetometers. So let's quickly go look at that video, see how this works. So the bottom left window shows how I play around and move these electromagnets. And the windows on the right shows the corresponding tracking result in real time. The way the system works is very similar to a GPS. So we know that in a GPS, to track the GPS device, you usually involve 2 simple steps. So first, if your GPS device, such as the mobile phones, need to first calculate distance from the device to the satellite that's running somewhere in the sky. And if your phone can perceive 4 or more satellites, the next step will be do a triangulation or trilateration to localize that. So that's a very straightforward 2 steps. So Finexus is exactly like that. But instead of tracking your phone, we are tracking the electromagnets. And those 4 satellites in the sky becomes 4 sensors on your board, which mark as S1 to S4 on the board. So again, 2 steps, very straightforward. First step will be calculate the distance between magnets and the sensor. So that will be from the sensor reading, and I'll quickly talk about this in just a few slides. So after we calculate the distance, the possible position of the electromagnets will be a sphere centered at the sensor, which mark like that yellow one. So the electromagnet can be anywhere on that sphere. So if we keep doing this on sensor 1, sensor 2, 3, and 4, so the outcome of this will be 4 spheres. And the intersection of them tell us where the electromagnets in the 3D space relative to the sensor. And this is fundamentally how it works. So again, this is very straightforward, very understandable approach, like GPS. The only question left here is how can we calculate the distance from between magnets and sensors from our sensor reading. So I won't go too much details here, but feel free to look out paper. But something I want to show here is a simplified equation. Where H is your sensor reading, that's something you retrieve from your magnetometer. And R is the distance between magnets and sensors. That's our target. So again, we don't have to memorize anything here. All details are in the paper. So here I just want to share some very high-level abstract and talk about what this exactly means. So intuitively, we convert the whole magnetic field space into a beacon-based system. And we treated each sensor as a beacon. So if you have some knowledge about this beacon system, we know that the signal strength perceived on a beacon is relevant to usually relevant to 2 variables. First, the distance from the signal source, where the signal comes from, and the receiving angle. And this equation is just a mathematical representation of this relationship. So this is, again, so I'll invite everyone to, if you're interested, read our paper, and we really show some interesting observations there. So fundamentally and theoretically, this should work. But in reality, there's some issue we need to deal with. So there are actually some ambient noise that we need to deal with. The first will be Earth magnetic field. That's some magnetic field on Earth. And also some electrical noise, or called EMI, electromagnetic interference, from the surrounding electrical device, like your keyboard, your mouse, LCD monitor, even your mobile phone. So they are a big problem. When the magnets move away from the board, this signal will become relatively stronger, and that's something we really need to take care of. In the meantime, we want to track a multiple of them. So to deal with this, we use frequency multiplexing. So intuitively, we drive this electromagnet at different frequency and use bandpass filter. So but allow me to quickly go through an example and show you how this exactly looks like. So this is the time domain data from z-axis of one sensor. So again, this is just data from one axis, from one sensor. So here, x-axis is sample and corresponding to time. Y is the magnetic field. So you can see that that's AC signals coming from all of these electromagnets. So this doesn't tell us much. So let's do FFT. So this is the outcome. So here, x-axis is the frequency, and y is the magnitude of each frequency component. So we can see 5 different obvious peaks here. They're corresponding to the signals from these 5 electromagnets. So I want to note that we have a very strong DC bias in the data, and this is coming from the Earth, so our mother Earth. So and you can see that the data is relatively bigger, actually significantly bigger than the signal we can leverage. So that's a problem too. We need to take it out. So if we apply a bandpass filter, for example, on 70 hertz, and the outcome of this will be the data not only attribute to one specific electromagnet. And in the meantime, we remove the Earth field because data becomes zero mean. So combine all these together, we can accurately track the motions of the electromagnets in 3D. So in this video, you can see that how I use the system for in-air writing. All right. So to prototype the system, we built a PCB board for that. So there, we assembled 4 magnetometers sampling at 450 Hz and include 3 microcontrollers on the board. And we also handcrafted these electromagnets. So each electromagnet had 300 turns of coil with a cover section of 0.25 centimeters squared. And also we use ferrite, it's a very cheap material for these electromagnets. And to drive it, we first synthesize the signal on a laptop and output to external audio card, amplify the signal, and then stream to the electromagnets. So I want to mention a little bit detail here that we do not run any frequency swipe to identify the optimal frequency band. All we care about here is to avoid 60 Hz and harmonics so we can stay away from those electrical noise. And of course, that's in US. If you're staying in Europe, this will be 50 Hz and harmonics. But it's configurable. So to evaluate the system, we use an optical tracker. So first, we put the markers on both electromagnets and your sensor board, and then compare the result from the tracker to our system. So the board was attached on the desk, and we moved the electromagnet around the sensor board to collect ground truth. So when the electromagnet move around, it is allowed to freely orient it in the space. So we can deal with different orientations. Within the volume of 30 centimeter cube, we collect around 90,000 data points in total for evaluation. And to evaluate the system, we consider 2 things, how accurate and how fast. So first, we report an average accuracy about 1.3 millimeter with 12 centimeter accuracy. So if you look at closer to the data, you can see that the performance within the 12 centimeters is kind of consistent. But once it's above the 12 centimeters, it's dramatically and significantly increased. The error increases. And this is because beyond that point, we barely hear nothing from the electromagnet because we leverage a very weak electromagnets. And so the field that we can leverage for is so weak. So that's why. And I'll talk a little bit how to extend this in the future work in just a few slides. So this is the accuracy. So how good the system will be. And how fast, but about how fast. So we report a computational cost for single data point at around 2.07 milliseconds. So we should note that the sampling rate, sampling period is around 2.2 milliseconds. So the time is smaller than the sampling period. So we confirm this system can run in real time. So this is our qualitative analysis about here. So at the end of the talk, I want to quickly go through the future work and something that we can potentially improve from the current prototype. So first, as I mentioned earlier, the board has 3 microcontrollers. And we do this just because we want to keep the system flexibility, just in case that in the future, we can put more sensors on that if we want to. But we realized that all we really need is just 1 microcontroller and 4 magnetometers, and that's all. So if we can remove these redundant components, we can shrink the board size to at least a factor of 2. So there are also a couple of things that I want to quickly mention here for improvement. So first, we still drive these electromagnets from laptop and those external audio cards you saw in the previous slides. So it is possible to build the other PCB board to drive this electromagnet so that the whole equipment can be completely wearable and more appropriate for mobile application. And so they can use them on the go. So second, I'm not a good engineer on making these electromagnets. So when I make them, I try my best to make it align and perfect. But still, the quality may vary. So that's why the size is still relatively bigger than now. So I believe that with decent training on mechanical engineer and some engineer effort, the size can be significantly reduced, and it'll be much smaller for now, better than now. And finally, it will also worth to try different sensors with higher sampling rate and also higher resolution. So to conclude, Finexus is a 3D input device that can track multiple fingertips and using only 4 magnetometers. And thank you. I'll be happy to take a question.
So thank you very much. Do we have questions? Yes.
Okay, Kent Lyons from Keller. Can you talk? Did you measure any of the power required to drive the electromagnets? Can you talk about that?
Yes. So again, we use a function generator to generate that the current. So we don't have the official number for that. But something that I'm certain and can share now is the field that we leverage for this. So we only, again, sorry, I don't have the exact number for now, but the field that we leverage here is only 1/16 of the Earth's magnetic field. That's what I can share for now. So again, I don't have the exact number, but I think that we have very, very small current and power. So that the field that we can leverage for so weak. Hi, Dan.
Hey, Daniel Ashbrook, Rochester Institute of Technology. I'm curious if you have ideas on how you can extend the range.
Yeah, that's actually something I really want to share. So yes, so they are part of the future work that we can potentially push. So the conclusion, I think it's totally doable to extend to 25 to 30 centimeter. So there are a couple of ways. First, the material that is used in the electromagnets is ferrite. That's very cheap. So I think the permeability of that material is about 32. So if you try to do some alloy or new metal, so the permeability where make you a stronger field, it's about 10,000 times stronger. So that's for the very effective way. So you just use a better material. And the second is the better effort on the engineer. So I'm really bad on that. So I do my best. So if that can perfectly align, the field will be stronger. So finally, I think the also very effective one, just use a different sensor. Because the sensor we are using here is from NSIC. So that you need to do a trade-off between the sampling frequency and resolution. So we try to do the good trade-off. But there's some other sensors that you don't need to do a trade-off. Higher frequency and a really good resolution to give you a very good perception of the field nearby. So even it's so tiny away from, you still can detect the differences. So I think that's 3 big things, and I think that's totally doable in the future. Yeah. Thank you, Dan.
Great work.
Thanks.
Okay, thank you very much. So once again, this is Honor.